All right, now we're going to keep going with our work in our counting unit, and specifically today we're going to be looking at permutations, and we're going to start with an introduction. Actually, we'll start with a couple examples, and then we'll get into our introduction of permutations, and then we'll do a couple more examples. So without knowing anything about permutations, let's try this problem right here. We have 4 different poker chips, red, white, blue, and green. And how many different ways can you arrange 2 of them in a row? All right, so we have 2 decisions to make, right? Which poker chip gets first and which poker chips gets second. So that means we have 2 slots, and everything's different, and we see this word arrange, meaning we care about the order. So that tells us we can just use the fundamental counting principle with the slots. So we have 4 options for the first slot and then 3 options for the next slot. So we have 12 different ways of arranging those poker chips. Not too hard of a problem, really just using the fundamental counting principle. But it's going to get harder. Okay, so same deal as the last problem, but now we have 13 poker chips, and we want to do 6 of them in a row. Okay, so let's go with it. So 6 different decisions, 4, 5, 6, and we have 13, 12, 11, 10, 9, 8, all being multiplied together. Okay, so we got some multiplication to do. 13 times 12 times 11 times 10 times 9 times 8 is 72. So that is 1235520. So 1.2 million just about. Okay, cool. So maybe you can imagine that the next problem might be we have 27 poker chips. How many ways can we arrange 19 of them in a row? And you can see things just get tedious, and we want a shortcut. We want a way to do it a little bit quicker. Okay. So I want to try something here. Let's get rid of this answer and just move it out of the way. And let's, in a separate color, pretend that we had kept going. 6, 5, 4, 3, 2, 1. All right, so that's just 13 factorial that I wrote out with an extra sort of 7 factorial tacked on. So I wonder if can you imagine doing this? Can we do 13 factorial and then let's divide away the 7 factorial? Okay, and can you see that that those 7 factorials will cancel, and we will just end up with the 13, 12, 11, 10, 9, 8. So this will equal 13 times 12 times 11 times 10 times 9 times 8, which is our answer. Okay, so if we can do the entire 13 factorial and then divide out the factorial that we don't want, we can get our answer a little more efficiently. So that's exactly what permutations does. And I'm going to write out its formal formula right now, but we have a lot of explanation to do around it in a second once I write it out. Before I explain that, let's make sure we need to use permutations when all objects are different, just like with factorial. You care about the order of the objects, just like factorial. But here you're not yet necessarily using all of the objects. You're allowed to only use some of them. Okay, so let's talk about this. N is the number of objects available. R is the number we're picking. So in the example we just did, we had 13 poker chips available, and we were picking 6 of them, right? Yep, we were picking 6. How do you read this, though? What do you say? And some people literally say NPR, National Public Radio, NPR, right? Some people say NPIC-R, okay? Those are the sort of the shortcut ways of saying things. The thing to keep in mind is that there's a clue, there's a code word here that we're going to start using, the word pick, And pick often refers to permutations, okay? In one of our next videos, we'll talk about combinations and we'll use the code word choose. So if you see pick or choose in this class in the world of probability, it usually means something particular. And here pick often means we're dealing with permutations. So let's fill in the information we have. Before we had 13 objects. We were picking, meaning we cared about the order, where all the objects were different, and we're not necessarily using all the objects. We were picking 6 of them. So it's going to be 13 factorial divided by 13 minus 6 factorial, which is 13 factorial over 7 factorial. So that bottom 7 factorial will cancel out. And I'm going to go to my calculator, and you'll see on mine, right above the number 1, I have an NPR. And so the way I'm going to type that in is I'm going to do 13 shift to access NPR, and then 6. And that equals the same number I had before, which is good. Good way to check, about 1.2 million. Okay. On your calculator, look for either the math menu and go to probability, or maybe there's a direct probability menu, but you should have a permutations button on there somewhere. Okay. So that's permutations are really just a shorthand of using the fundamental counting principle or factorial when we're not using all of the objects. Let's look at people in our class. There are 26 people in our class. I want to line up 7 of you in a row in front of the room. How many ways can I do that? So let's go back and check to make sure we can meet all the criteria for permutations. I'll just bring this guy down. Whoops, didn't copy the text. Let's see here. If I can copy the text, maybe it won't let me. Okay, I am going, oh, maybe I can copy. Let's see if I can do that here. Oops. Get rid of that, and let's try to paste some stuff. Okay, cool. So we got it. So let's check to make sure permutations are allowed here. So are all objects different? Yep, all 26 people are different in my class. Do I care about the order of the objects? Yes, I do. I'm using this word line up, and that really means that I care about the order in which you line up. And you're not necessarily using all the objects. That's correct. I'm only using 7 of them. Okay. So let's go ahead and do it, and we are really just going to do 26 pick 7. Okay, and that ends up being another big number. Okay, so we can throw in our commas right there, and in that case we have about 3 billion ways of arranging those 26 or those 7 people out of the 26 in a row. All right, and my last one for this video, I borrowed 8 stuffed animals from my kids for a stats experiment. If I want to arrange 6 of the 8 animals in a row, what's the probability that the stuffed wombat is first in line? Okay. So I want to get 6 in a row, and so I'm going to do my definition of probability equals, it's a quotient, right? So this has the wombat first, and this just has any 6 stuffies. Okay, so let's figure that out. So for the bottom, I think the denominator is a little bit easier. It's just going to be 8 pick 6. Okay, so we have 8 of their stuffed animals to choose to pick from, and we're picking 6 of them. For this top one, let's imagine having our 6 slots laid out. This guy has to be the wombat. Okay, we want it to be the wombat. He really has a stuffed wombat, by the way. This is going to be 7 pick 5, because now we only have 7 stuffed animals left, and we only need to pick 5 of them. Okay, so we can do both of those permutations. 7 pick 5 is 2520 divided by 8 pick 6, which is 20,160. We just do a quick division. 2520 divided by, I get 0.125, which is 1 out of 8, about 12.5%, exactly 12.5%. You might wonder, that's curiously exact. Well, we had 8 stuffed animals, right? And one of those 8 has to be the first one. One of those 8 has to be in that slot. What's the chance it's the wombat? It's 1 out of 8. Okay, so another way of thinking about the problem. All right, that's a good place to stop right there.